Okay, so here we are, class number 3. Before I get into content, I wanted to say something about the quiz as far as procedure goes for today and for the future. Didn't pay as much attention to this last Thursday, but today, again, if you do need to step out after you're done with the quiz to use the restroom or whatever, please do bring your quiz up with you, so I'll take it. And again, if you're late to class and coming back, then points get deducted, and so that's my way of trying to help you keep on time and getting back. Although if you, again, you're not feeling well, then that is an okay thing, and you won't get the points deducted then. Second thing is I saw many people whip out their phones after they were done with their quiz, and you have the quizzes turned over, which was good, but I think if you're going to whip out your phone and play on your phone or something, I am going to want you to turn your quiz in if you just can't resist using your phone. I will let you, but raise your hand, I'll come and get your quiz from you, and then you can use your phone if you want. Okay? So a couple of procedural things about that. All right, so you can see the topics there for today. And as usually will be the case, it's quite a number of topics. Computing standard deviations on spreadsheets, density curves and simulations on spreadsheets are going to be in lecture A, and you're going to have two things to do on a spreadsheet for Thursday's assignment. I think once again you can either download what you do on Google Docs spreadsheets, either into Excel or as a PDF. More ideally it would be Excel if you can. If you don't have Excel on your computer, you can use one of Bethel's computers before you upload it onto Moodle. So you'll have a couple things to do there. And in lecture B, we're going to do a harder topic about normal curves and using table spreadsheets and calculators to do normal curve problems. Now you have a little bit for this assignment, relatively easy problems with normal curves. It's going to be harder for the next assignment. This assignment due Thursday is going to be more difficult than most assignments, well, than the assignments we've had so far. I am here to help, and even though lectures feel in person, well, I do care about you. Even though I don't know most of you personally, you are my brothers and sisters in Christ, and so I care for you even though I don't know you. I want the best for you, and I want to follow Christ's command to love each other and look out for each other's needs, and I want you to do so too. Here's the command in John 13, a new commandment I give to you, that you love one another just as I have loved you, that you are also to love one another. By this, all people will know that you are my disciples if you have love for one another. So you care about each other, you care about each other's interests. You work together, you help each other. Again, that doesn't mean copying, it doesn't mean cheating, but you help each other to the best of your abilities. You pray for each other, encourage each other, and I will try to do the same from my perspective too. I will try to encourage you as best I can. On the flip side, I do have a job as a teacher to also grade you, to assess how you're doing, and so those sometimes feel like they're in conflict. But I do want the best for you. I do want you to be able to do as well as you can. So feel free to come to me if you have any issues you'd like prayer about in addition to math questions. And maybe the prayer is about math. Okay. So first I want to focus on standard deviations.
Sorry, I just have a quick question. How often will we be getting our homework back?
Well, I'll give this to the grader here today, and hopefully they can get it back by Thursday. Ideally tomorrow even.
Okay.
So we'll see. So we're going to first focus on computing standard deviations. I already mentioned that you can use equals STDEV as a built-in function of a spreadsheet to calculate a sample standard deviation. And again, we call that S. On the calculator, in stat mode, it is an S. And again, I'll show that to you here now. So let's see here. Stat mode, do we have any numbers? Yes, we've got some numbers in there. You go to calculate, one variable stats. Again, maybe your calculator doesn't look like this. I hope it's not too far off. Something like this. When I go to calculate one variable stat, and if it's in a list 1, I don't have to type list 1, I can just hit enter. I get some statistics. I get x bar, the sample mean, and I get an S right here. S sub x, the standard deviation of the x values about 12.74 in that case. Ignore this thing, ignore this sigma. We are going to use this symbol for the standard deviation sum today, but it's not going to be for data. Okay? So we ignore that, we just use the S. So that's how it goes on a calculator. And you use the formula in addition on this assignment to calculate the standard deviation. I'm also going to want you to be able to use the formula on a spreadsheet, and that's what I'll show you here in a minute. Once again, I wanted to use Mathematica to illustrate some things like this visual interpretation of the mean as a center of balance, but I put a request into Bethel's tech services and they still haven't fixed it. So I still have to delay this. But here's the formula for the standard deviation in all its glory. Let me write it on the board. I'll write it in sort of the sloppy form here with the summation. Again, that second form with the summation is sloppy, but we'll be okay with that. We take the square root of 1 over n minus 1 times the summation of a bunch of squares. Summation, that means add. These are a bunch of squares. You take the x values, the data. For each one of those x values, you subtract the sample mean, square that difference, add those up, divide by n minus 1, and then take a square root. It's important that you understand the order of operations. So you made a little table by hand for one of your homework problems. You should have to use this formula for today. Let's do the same kind of thing on a spreadsheet, and you're going to have to do this for your assignment as well, part of your electronic assignment for Thursday. So I will do an example. I will make some data first of all. Just make up some numbers. 5, 8, 10, and 14, say. It's good to calculate the mean first. We need the x bar in the formula. Notice there's the x bar in the formula. You're going to need that if you're going to calculate the standard deviation. I'm fine with it if you want to just use this built-in function equals average to calculate that mean. Which I don't remember if I showed you that before. I might have done equals sum before and then divided by 4. But typing it like that, equals average, and then in parentheses put the cell references for your data, which is behind this thing here. Let's X that out. You can highlight that, or you can just type, in this case, B4 colon B7. That will refer to those cells, B4 through B7. You actually don't have to use the end parenthesis. There's the mean, 9.25. We're going to need that formula for the formula. These quantities that you see in here, x minus x bar, those are called deviations from the mean. They have a name. Deviations from the mean. Okay, go ahead and label the next column deviations from the mean. I'll just abbreviate like this. Let me get that up close so we can see that. Part of the reason I'm having you do this is to get a little practice with the spreadsheet and some built-in spreadsheet functionality. What I want you to do here next, this is the trickiest part perhaps, is I want to take each of these x values and subtract that mean. Here's the quickest and best way to do that. Let me just type it first and then I'll explain it. In that cell that you see right there, cell C4, what did I type? I typed equals B4 minus B9, and I put dollar signs sort of around the B in the second. Actually, more accurately, it's a dollar sign in front of the B and a dollar sign in front of the 9. By using the dollar signs, that's going to keep this cell fixed, 9.25. That value is always going to be subtracted. By not using the dollar signs there, that's going to keep this cell reference not fixed. When I copy and paste this formula, as I'm about to do, down to cell C5, then C6, then C7, that part of the formula will get updated to B5, B6, and B7. I want to take these different x values, but this part will stay the same. The B9 will stay always at 9.25. This will stay at B9. Actually, you can get away with just putting a dollar sign in front of the 9 in this case, because we really just need to keep the row fixed, and the B would automatically be fixed. But to play it safe, put dollar signs in both spots. You understand the basic idea there? The B4 again is going to refer to the number in cell B4, the 5. So you're going to take 5 and then subtract the number in cell B9, which is 9.25. Since there's no dollar signs with the B4, that cell reference will get updated as I copy and paste the formula downward. The dollar signs for the second one don't. And I don't want them to. I don't want them to change to B10, B11, B12. So this first one's going to be 5 minus 9.25, which is negative 4.25. Copy and paste. You can do a Control-C, Control-V. That's one way to copy and paste. Double check that that's right. 8 minus 9.25 is negative 1.25. You can also click and drag. Once you've got this cell here like this, you can click and drag the lower right corner to copy and paste. Double check these. 10 minus 9.25 is 0.75. 14 minus 9.25 is 4.75. Some of these are negative, some are positive. And in fact, if you add up the deviations from the mean, you'll always get 0. It should be somewhat intuitive that the distance of these numbers from 0 is some sort of measure of the spread. Standard deviation is supposed to measure spread. But if you average these numbers, you'd get 0. So that's not very helpful. One way to get rid of those negative signs is to just take absolute values, though that's harder to work with symbolically. So what we do with these instead is we square them. Square deviations from would be the next column. What do you think I should type here in order to do this efficiently? What should go in cell D4 to do this efficiently? Certain cell reference, C4 squared, like that. Oops, like that. That's going to take what's in cell C4 and square it, which is what you want to do. You square those deviations from the mean in the formula. And since I'm not using dollar signs, that formula will correctly get copied and pasted as I go down to D5, D6, D7. It will become equals C5 squared equals C6 squared equals C7 squared. Watch it here. I'm going to square all those numbers. When I click and drag, yes, 1.25 squared, negative 1.25 squared, for example, is positive 1.5625. And you can also see if you look up here, when you click on cell D5, that formula equals C5 squared is correct. It got correctly copied and pasted, and you changed the cell reference, which is what you want to have happen. What's the next thing to do in the formula? Add up those squared deviations. Now we can use equal sum. Add up those squared deviations. Divide by n minus 1, and then take a square root. The standard deviation, I'll just do in one step now. You think this is fine for you too. You can do it this way. Take the square root, which you can do with SQRT, or when you raise to the 1/2 power is another way to do it, of this thing divided by the sample size minus 1, n minus 1. N is 4 here, so divide by 3. I'll type it in as 4 minus 1. Actually, if you don't know what n is, there's another function called count that can be used in place of the unknown value that will count how many data values we have. But in this case, it's nice and simple. We've got 4 data values, so n is 4. We've got to divide by 4 minus 1, which is 3. The standard deviation is 3.7749 approximately. And then you can double check it with the built-in equals STDEV. Highlight the original data, like that, and enter that. It should be the same number. And you can see it, it previews what the answer is going to be, 3.7749. Okay? So you will be doing a problem similar to this for your assignment as part of your the electronic portion of your assignment. You'll be doing one other thing that I'll show you in a little bit. Can I clarify anything there? Okay, you just take it step by step. Question?
That last part you said with the sum, can you repeat what you said? Yes, sir.
So for this cell right here, I did equals SQRT, the square root of D9, which was right there, which represented the summation I divided it by 4 minus 1, n was 4, so I'm dividing it by 4 minus 1, which is 3. You could type it as a 3, and then taking the square root. That's what the SQRT does. You also could do the whole thing to the 1/2 power. That also does the square root.
Okay.
Okay? And you can check it with your calculator if you want to make sure you're doing it right. What's another benefit of this besides practicing a little bit of it with Excel? You can experiment with it to see why it gets bigger, for example, when your data gets more spread out. If I change this 14 to, say, a 24, since I use formulas, everything's going to get updated correctly. The mean will go up. It's not resistant to outliers, but also the standard deviation will go up. Watch how things change here. Ready? 1, 2, 3, go. See that? I'll do it again. Here's the original one. Watch these numbers. Everything will get changed. Especially focus on this number that I'm changing, and that number, and that number. Change 14 to 24. What happens? Ready? 1, 2, 3. Focus in on the video. Go. That number got a fair amount bigger, further from 0, and that number, the square, got a lot bigger. The mean got bigger, the standard deviation got bigger. The data are more spread out. If I go even more extreme and do, say, 2,400 here, then it gets really extreme. Everything involving that, and that get a lot bigger. In fact, everything else gets a lot bigger because the mean got so much bigger. Okay? That's another benefit of doing it this way on the spreadsheet, is if you play with these things enough, you can get some understanding of why this is a measure of spread in this case. Okay? All right, let's go back to the PowerPoint. So I gave you the purpose here, and I'm just reiterating it here. Purpose to gain some spreadsheet skills, which we'll need later in the semester, and to get an intuitive feel for how changing values in the data set affect the mean and standard deviation. That's what we just saw. That was the purpose of what I was doing. All right, you read a little bit about density curves, and density curves could show up on the quiz today, or perhaps the quiz on Thursday, or later in the semester. I want to illustrate the idea of a density curve before I describe what they are. I'm going to use a spreadsheet, and this is going to be related to your other part of your electronic assignment. I'm going to use a built-in function called ran in the following way, equals 10 times ran, on a spreadsheet over and over again to produce data. Really, it's fake data in a sense, it's simulated data, consisting of a bunch of random numbers between 0 and 10, fractions included, decimals included. Mostly they are not going to be integers. They're not going to be whole numbers. And I'm going to make a histogram of the data. In fact, I've already done it. Because of random variation, when I do that, the bars that I get from the histogram are not exactly the same height. However, they are roughly the same height. Okay? I did it once on a spreadsheet. I used this 10 times equals rand, which generates random numbers. Rand itself generates numbers between 0 and 1. By multiplying it by 10, I'm generating random numbers between 0 and 10. And I got that data. In fact, I think I had 500 data points, if I recall correctly. And I made a histogram. There were approximately, if you look at the scale here, approximately 40 numbers that were between 0 and 1. There are approximately maybe 62 or so numbers between 1 and 2. Got to make sure you can read histograms. There were approximately 60 numbers between 2 and 3. Approximately 55 numbers between 3 and 4. Maybe about 51 or 52 numbers between 4 and 5. You see how that works? I'm counting the frequency. How often does each number go into each interval, each bucket, or each class? That's what I got. And again, the bars aren't exactly the same height. And you shouldn't expect that they'd be exactly the same height because of random variation. This is a very fundamental thing to realize. However, they're approximately the same height. It should make sense in a sense that, no pun intended, that happened accidentally, right? It's not a pun intended if it happened accidentally. It should make sense in a sense that all numbers are equally likely if this random number generator thing does its job. There's an idealized histogram you could make. It's not really a histogram. That would model the situation. It's called the uniform distribution. This last set of data can best be modeled by something called the uniform distribution. It's a horizontal line. It's uniform. If we label the vertical axis with relative frequencies as percent, say, rather than counts, the uniform distribution is an idealized graph that models a generic histogram generated with that spreadsheet code equals 10 times range. It's a horizontal line. Essentially, we're saying, ideally, if you did this over and over again, these histograms are going to be well modeled, on average, by this horizontal line, where you could think of it as a bunch of bars of the same height, if you prefer. Does that really happen? What do I mean? We can use the spreadsheet to find out. I did it already. Here we go. I used equals 10 times rand. Nothing needs to go inside the parentheses for the rand, by the way, if you were wondering. To generate a bunch of random numbers. Okay, look at the formula. Equals 10 times rand. Rand again generates a random number between 0 and 1. Multiply it by 10, you effectively get a random number between 0 and 10. How many of these numbers are there? There are 500. That is the 500th number. It's in row 501 because in row 1, I have the column heading, use equals 10 times range. And I got this graph. That graph is different than the graph I already showed you in the PowerPoint. Because every time you hit enter in one of these, everything changes when you use rand again. Watch it. Ready? 1, 2, 3, go. Oh, hi, my face. Okay, type something over here. There's my mistake for the day. Type it over here just for fun. Watch, now everything will change, I promise. What? Oh! What in the world? It worked on my computer again. I can't believe it. Did it change? Okay. I saw the first number, I didn't see it change.
You can't have a meltdown on YouTube, I'm sorry.
Okay, I just didn't wait long enough. It was like a half-second delay. That's the problem. Oh my goodness, I'm going crazy. Now watch it, it's like a half-second delay. And I only saw that first half second. I said, oh, it didn't change. Okay, yeah, it did change, okay. And watch, and yes, the graph changes as well. Every time you use it, the graph changes to reflect the new distribution. Did it change everything? Pretty cool. The graph should be changing. Is it not changing now? What did I do differently? Okay, I am going crazy.
It changed the first time you did it.
There we go, okay. I don't know what happened there. Anyway, every time you use it, the numbers change, the graphs change as well, but they're all still relatively the same, okay? Doesn't like it unless I retype it. Or I need to retype it in a new cell. Okay, whatever. Okay? So that uniform distribution is idealized. Here's another example. Use rand again, but this time, let's do equals 5 times rand plus 5 times rand. Now again, rand produces a random number between 0 and 1. I'm using it twice, and each time I'm multiplying by 5. Shouldn't that still produce random numbers between 0 and 10 that are sort of evenly distributed? The answer is no. It has a definite pattern. Now that pattern is a pretty symmetric pattern. You might say it looks like a bell-shaped curve, but actually it looks more like a triangle. If you do it over and over again. And let's do it over here. I've got use equals rand, 5 times rand plus 5 times rand over and over again, here again. Most of the numbers are fairly close to 5. There's very few that are down near 1 or up near 9, relatively speaking. Here's another graph. Okay, if I do equals rand here, it should change, get updated. Ready? 1, 2, 3, go. It changed, but it's still got a symmetric pattern, and it's definitely not uniform. And you can do it over and over again, you see the same thing. So that's a different kind of distribution, a different kind of density curve to model it. And actually, I mean, you could try using a normal curve to model it, but it's better in this case to actually use a triangular distribution that looks like that. The graph looks like a triangle instead of a horizontal line. You should have read about this. This did come up in the reading, by the way. Not rand, but these graphs. You still want to make the area under it equal to 1, which is, I think, I forgot to say this. I'll go back to the other one here in a second. The total area under this was 100% or 1. Thinking of these vertical axes as being percentages, the area under that graph, it's a rectangle, this base times height is 10 times 10 is 100. 100%. Percent means per 100, so when you say 100%, you're really saying 100 divided by 100, so 100% can be thought of as 1. In this next graph, in this slide now, instead of labeling the vertical axis with percents and labeling them as decimals, you could convert them to percentages. This 0.2 could get converted to 20%. But more often, we're going to label a relative frequency as a decimal. Now the area you truly think of as being 1. The area of a triangle is 1/2 base times height. The base of that triangle you can see is 10, and the height is 0.2, which is the same as 1/5. You multiply 1/2 times 10 times 0.2, you will get 1. The total area under that graph is 1. Density curves have two fundamental basic properties. They never go below the horizontal axis. They're always on or above the horizontal axis. And the area under them, total, is always equal to 1. Those are the two most basic and important things to know about density curves. This uniform one and this triangular one are two examples, two fairly simple examples of density curves. What's their purpose? What's the reason we have these density curves? Initially, I'm just saying we're using them to model histograms, like these histograms that I made on the spreadsheet with rand. Okay, but it also could be histograms for real data. More important. The key to using these distributions is this. This is very important. When you want to know an approximate percentage of data values in a certain range with a given density curve as a good model, you, in boldface and italicized, calculate the corresponding area under the curve. For example, if you've got a triangular distribution like the one I showed you, this graph looks like a triangle. This is supposed to be a straight line there. This is 10 right there. This graph never goes below the horizontal axis. It's always above or on the horizontal axis. You ignore it outside of this range between 0 and 10, or else you think it's 0 outside the range. It's supposed to represent a histogram for some data, let's say, an idealized form of a histogram, the shape or pattern of a histogram. And if you want to use the density curve to, for example, approximate the percentage of data that's, say, between 6 and 9, you need to calculate the area under that curve between 6 and 9. What is this area that I'm shading right there? The percentage of data with values between 6 and 9 is approximately the area of this trapezoid there. The trapezoid. The area of a trapezoid can be found by taking the base, which is 3, times the average of the heights. This height right there and this height right there. That's one way to figure out the area of the trapezoid. Another way is to split it into a rectangle and a triangle and add those two rectangles. Okay? I don't want to say you should memorize formulas. I mean, you should for quizzes, like today's quiz, those formulas we've seen. But for tests, probably I'd prefer you, if you're unsure, if you don't have the formula for the area of a trapezoid, you should think of it as made up of a rectangle and a triangle. What's the height of this rectangle? That's a little tricky. Since these are straight lines and the total change in the y direction along each straight line is 0.2, each time x changes either from 0 to 5 or 5 to 10 by 5, that's going to mean each 1 unit increase in x corresponds to a change either of positive, let's see, take 0.2 and divide it by 5. 0.2 divided by 5 is 0.04. So you have either positive 0.04, each change of x by 1 unit increases y by 0.04 as you move to the right when you're between 0 and 5, and each 1 unit increase in x as you move to the right when you're between 5 and 10 decreases y by 0.04. What that means is, since 9 is 1 unit from 10, that means the height right there is going to be 0.04. And since 6 is 1 unit from 5, that means the height right there is going to be 0.16, 0.2 minus 0.04. I said that kind of fast, and it might have been kind of confusing. That's something you may want to rewatch. I'll say it again, though. You know, it's effectively related to the slope of these lines. For example, the slope of this line, rise over run, is 0.205, which is 0.04. That means for every 1 unit increase of x, y goes up by 0.04. On the flip side, because of the symmetry, the slope of this one is negative 0.2 over 5, which is negative 0.04. So each time x goes up by 1, y goes down by 0.04. Since y is 0.2 when x is 5, y has to go down by 0.04 to 0.16 when x is 6. And that's the height of this thing right there. The height of that side of the trapezoid. Since 9 is 1 unit away from 10, the height of this one's got to be 0.04. Anyway, what's the area? If you want to think of it as the area of a rectangle plus the area of a triangle, the base of the rectangle is 3, the height is 0.04. So 3 times 0.04 is the area of that rectangle. The area of the triangle is 1/2 base times height. The base, once again, is 3. The height here is 0.16 minus 0.04. This height right there is 0.12, in fact. This 0.16 refers to the entire height. The 0.12 refers to this part of it. You know, it's not real clear from the picture. So 1/2 times 3 times 0.12. That's going to be the area of that triangle. If you do this, you get 0.12 plus what? 1/2 times 0.12 is 0.06 times 3 is 0.2.